All right, so what we're going to do now in this lesson is we're going to be talking about ultimately adding, subtracting, multiplying, and dividing different functions and its resultant domain. So this is pretty much for adding functions, and this is the rule. It says if I add a function, f plus g of x, I can write it kind of in this weird way here that just simply says f plus g of x. And this is just a different notation, kind of shorthand for saying, hey, I want to add my f and my g. And the domain, well, it's kind of this rule. What the domain of an addition problem is saying is the resultant domain will be all the elements of f and all the elements of g. And the easiest way to think about that is where do these domain overlaps occur? So it's an overlap. It's the domain of this and the domain of this. It has to be the set for both. So let's see what that looks like. All right, so we're going to find the sum and then determine the resultant domain. Well, we have f and g, and what I want to do is I just want to develop kind of a system of how to think about this, because ultimately, in the end, we're going to think about its resultant domain. So in order to be thinking about this ahead of the game, is we're going to start by writing the domain for each function and just identify these are both linear. So that has a domain of all real numbers, and that has a domain of all real numbers. So I know that when I add these, which is the next step, I'm going to bring my f down and my g down. Now I put those in parentheses. They're not required to be in parentheses when it's addition, but it's a good habit when this becomes subtraction. Notice that subtraction would be distributed of whatever was over here. So just out of habit, I put those in parentheses. And now the only thing I've got to do now is think about combining like terms. 2x plus 4x is 6x. That minus 3 comes down. So this is the sum of f plus g. And then it's also linear. So, of course, we could just jump over here and say, well, then the domain should be all real numbers. But we are, in essence, thinking about where does this overlap? Of course, it overlaps everywhere. So there's the domain of that resultant function. Okay, let's look at another one. Now I've got the sum of f and g where they're both quadratic equations. Again, step one, let's think about what's the domain of all quadratics. So this would be all real numbers, all quadratics, all real numbers. Step two, let's write this as a sum. So f plus g of x. And then let's bring these down into an addition problem. I did the same thing. I put them in parentheses. The second step is just to identify that we could, in fact, reorganize this. Notice my 2x plus my 5x squared right there. I had a linear, which was 3x. I brought that right there. And I put my constants together. And I just wrote this in descending order, where that's second degree, first degree, 0 degree. And then I can combine these and get the answer of 7x squared plus 3x minus 9. And the same thing, I want to know what is the domain of the resultant. Well, the domain should be the overlap of all real numbers and all real numbers. Well, that's simple. All real numbers is the domain of this f plus g of x. Okay, let's look at another one. In this particular, I just got a little bit goofy. So we have f plus g, but we have a second degree polynomial and a third degree polynomial. So let's think about those domains. All real numbers and all real numbers. So again, this becomes kind of easy. When the domain is all real numbers, of course, the resultant should be all real numbers, unless it's a division problem. We'll get to that in the end. But let's set up the function f plus g of x. Let's bring these down. And the next thing I'm going to do is just reorganize in descending order. So start with the highest degree and reorganize. So there's my third degree. I had 2 second degree, so I put those together here. I have a first degree and 2 0 degree. And now we can just say, well, that's the only one. That should be a part of the answer. Let's combine these. That's the only one, and let's combine those. We should get 5x to the third plus x squared minus 11x plus 3. So the resultant of adding a second and a third degree is a third degree polynomial, which has a domain of all real numbers because that is the overlap in all real numbers. Okay. All right. No big deal. Let's get a little bit, let's kind of branch out and start using some different functions that aren't just polynomials. So now we've got some radicals. I kind of think about this a little differently. I don't want to just write the domains. I want to show you their graphs and then see if we can pull the graphs or the domains from the graph. So let's graph this one first. So there's the parent function for the square root of x. It started at 0 and went to infinity. So there's the domain, 0 to infinity. We get to include the 0. And what would this graph look like? Well, this is the parent function moved to the right 4 places. So if we graphed that, we could think about its domain as 4 to infinity, including the 4. All right, now let's do the next step and think about the sum. So f plus g could be written the square root of x plus the square root of x minus 4. And I mean, this is the easy part, because in this particular instance, we can't do anything else to this. Like this is like x plus y. They're not the same term. You cannot add them together. You just got to leave it like that. So that is the sum. And let's think about the domain. The domain is where these graphs overlap. Well, they're going to overlap here and over. So they're going to overlap from 4 to infinity. And that is the domain of that graph or that function. All right. Let's think about a reciprocal added to a linear. Let's do the same thing. This was a parent function. We kind of memorized the domain of that, which was negative infinity to 0, 0 to infinity. Notice that this was a domain restriction. X could never be 0, so there it is. And this was all real numbers. So let's look at the addition. F plus g of x is going to equal 1x plus 2 of x, and then notice, or 2x, not 2 of x, and we need a common denominator. So let's put this over 1, and then identify the common denominator has to be x. So I already had the x, so times 1 times 1. This was missing the x times x times x, and that produces 1 plus 2x squared over x. And again, we can look at this and say, hey, that can never be 0. But if we thought about the overlap in those two functions, the overlap is every number but 0. That makes sense. There's the graph of that function. There's the graph of that function. And you can see every x is shared except 0. So there's the domain. There's the domain of f plus g. Every number but 0. All right. So let's look at subtracting functions. Now this is going to behave the same way. We have f of x minus g of x, or it can be written f minus g of x. Same thing, just again, shorthand for this. The domain is treated the same way. We need all elements of f and g to be the resultant domain. So let's look at a few examples. So again, let's think about, because we want the resultant domain in the end, I always think about, well, what's the domain of that? It's all real numbers. It's linear. It's also linear, all real numbers. And then we can go into thinking about the subtraction. Let's bring this down, minus this. Now these parentheses are really helpful because we do have a negative to distribute. So let's distribute that. And what is that going to give us? 7x minus 3 plus 7x minus 8. We could reorganize these if you want. But that is 14x minus 11. So there's the resultant function. But what's the resultant domain? Again, it's where do these overlap? All real numbers overlaps with all real numbers. The domain is all real numbers. All right. So let's do this one. I have a quadratic, and of course we're going to take the difference. So I have a quadratic minusing a quadratic. I want the resultant domain. So let's think about what's the domain of all quadratics and what's the domain of all quadratics. Well, they're all real numbers. So let's show the difference. Let's bring this down minus this. And again, let's distribute this negative. Well, the only thing left to do is reorganize. You don't have to reorganize, but it is the commutative property of addition where we can move things around. Even though it's not addition, it's subtraction, the commutative property works the same way. So let's reorganize our second degrees, our first degree, and our 0 degree. And we would get something that looks like that. Notice I put my x squareds together here. I kept that minus in front of the 2. I brought that first degree. It's the only one. Oh, that's wrong. There's another first degree. And there was only one 0 degree. I put it right there. So if we combine these like terms, we have negative x squared minus 4x minus 3. And the resultant domain, well, it should match the domain of a quadratic, which is the overlap of both of those. All real numbers. Okay. Now these have domain restrictions. These are the ones we really want to spend our time on, at least for the resultant domain, because that's the challenging part on when there's domain restrictions of what's the domain after the fact. So again, let's think about step one, about writing these individual domains. And I want to show the graphs first. So well, where would this graph be? Well, this is the parent function moved to the left 3 places. So it's right here. So that should have a domain of -3 to infinity. And what was this one? Well, this is the parent function moved to the right 1 place. So let's put that one here. And that should have a domain of 1 to infinity. Okay, that's almost the hard part of this problem, because if we do step 2, which is just set up the subtraction, there's your f minus g. And since they're not the same term, I mean, that's the answer. Might as well circle it. Smile. Only thing left to do is determine its domain, which is why I graphed them, because if you graph these, you can see the overlap is from 1 to infinity. And that is the resultant domain of this graph. The only domain that's acceptable is 1 to infinity, because it's the only values they both share. Okay? And let's think about subtracting a reciprocal translation and a linear function. So let's set this up. Think about, well, what is the domain? This graph, this reciprocal graph, is being moved to the right 2 places. And if you didn't know that, you could still at least look and say, what is this? What could x can never be here? X could never be 2. And we could at least come up with the domain of every number but 2, because this can never be 0, and 2 is the only thing that makes that 0. And what's the domain of a linear? Well, it's all real numbers. And the resultant domain of this subtraction is going to be the overlap of these 2 domains. Let's set this up. Let's bring these both down and subtract them. Notice they're missing a common denominator. So let's go get it. The common denominator should have been x minus 2. This already had it, so that's times 1 times 1. This is missing the x minus 2, so I multiplied top and bottom by that. If we work this out, we get 1 minus 5x squared plus 10x. And again, the only thing to do here, which I would personally do, is I would rearrange the numerator in descending order by putting our second degree first degree, and then follow the 0 degree, which would be right there. And again, we can look at this and say, what value is not acceptable here? Well, it can't be a 2, and that is the overlap between those. There's the graph. There's this graph. You can see that every x on both graphs is shared except at 2. So there's the domain, negative infinity to 2, union 2 to infinity. All right, let's look at multiplication. Here's f times g, which could be written f times g of x. So there again, there's just the shorthand. And the luxury is the domain is absolutely identical than it was for adding and subtracting. It's all elements of f and g. Again, we just want to know the domain overlap, the overlap between the domain of f and the domain of g. So let's do a few of these examples. And I've got several here. I apologize for the length of this video, but I really wanted to give you multiple opportunities to see different problems solved. So let's think about, again, just staying with knowing we need a resultant domain. So let's think about domain of a linear is all real numbers. Domain of a linear is all real numbers. This is the easy one, right? The domain of this resultant is going to be all real numbers. But what is the function f times g of x going to give me? So let's bring these both down into a multiplication problem. And you've got 2 options. Of course, you could FOIL this, first, outer, inner, last. Or I'm going to show a table just in case it's not just a 2 or a binomial times a binomial. So I'm going to set that up in a table. Where I put on down here, I put my 5x, my -3, my 6x, my -2. And I can just multiply this here. 5x times 6x is 30x squared. 5x times negative 2 is negative 10x. Multiply the negative 3 times the 6x, negative 18x. And a negative 3 times a negative 2 is a positive 6. And if we use a table to do this problem, what we want to do is we want to add. And I'm going to say that again. We want to add diagonally. Since there's only one number here, there's nothing to add. But then I'm going to add these, and then I'm going to add that. So we can go over here and say, well, 30x squared is the only second degree. It gets to be a part of the answer. But if I add negative 10x and negative 18x, I'm going to get negative 28x. And that positive 6 was the only one there. So there is the resultant function of f times g of x. And the domain, like I said, that's the easy part because it's the domain of an overlap of all real numbers, which is all real numbers. And this table will make a little bit more sense, hopefully, when we do the next problem, which is the product of a trinomial and a trinomial. Three terms. So let's think about, because I want the resultant domain in the end, let's just do step one. What's the domain of all quadratics and all quadratics? So that's, again, this is kind of the easy part. The domain's the easy part on the ones that have no domain restrictions. So let's set up the multiplication. F times g of x is going to equal f times g. Now, this one becomes a little bit more messy when you talk about, multiplying here and here and here, and then multiply here and here and here, and then multiply here, here, and here. Some of you will do it that way. I'm going to generate this table and bring these three terms and line them here, and then bring these three terms and line them on top. And now it's a little bit more organized to say, well, what's x squared times 2x squared? Well, that's 4x to the fourth. X squared times x, x cubed. X squared times negative 1, negative x squared. Let's jump to the x and then multiply here, here, and here. So x times 2x squared is 2x to the third. X squared, negative x, negative 8x squared, negative 4x, positive 4. Now my table is filled in. We can add diagonally now and answer this question. So again, here we are, 2x to the fourth. It's the only one there. I add these, 2x cubed plus x cubed. I get 3 of them. I add diagonally here. I get negative 8x squared plus x squared, which is negative 7x squared, minus x squared. That's negative 8x squared. And then add negative 4x minus x, negative 5x, and that 4 is all by itself. This is the resultant of a second degree times a second degree. We get a fourth degree polynomial, and its domain will be the overlap between those two, which, like I said, is the easy part because it's all real numbers. All right, let's think about what if I was multiplying radicals. And let's think about this domain first. This was the parent function moved to the left 5 places, so its domain should be negative 5 to infinity. This was the parent function moved to the right 7 places. It should have a domain of 7 to infinity. Again, the reason to do that, these graphs help with these radicals. And also when I want to do the domain overlap, I can see where it overlaps. And let's set up the multiplication. And in this case, this isn't like the addition and subtraction, where I was just like, well, write it as plus or minus and you're done. Here there is something to do. Because it's a radical times a radical, I can multiply x plus 5 and x minus 7 inside the radical. You can get the square root of x squared minus 2x minus 35. That is the quantity of x plus 5 times the quantity of x minus 7 inside the radical. So that is the answer for this product. What's its domain? Well, the domain should be the overlap of these two domains, which is right from here to the right. So 7 to infinity is the overlap. And that's the domain of f times g in this particular example. All right, well, let's talk about a reciprocal translation times a reciprocal translation. And let's set up the domains. X could never be 2, so let's write that. And X could never be -4, so let's write that. And let's set up the multiplication. F times G of X is going to be F times G. And this is an easy one, right? Because we can multiply straight across the top and get a 1. And we can multiply straight across the bottom here and get the quantity of X minus 2 times X plus 4, which is X squared plus 2X minus 8. And the domain, what's the domain? Well, the domain is going to be the overlap of these two domains. And there's the graph. It's kind of an example. Well, if I took this graph, which is in red, and I took this graph, which is in green, you can see that every X is overlapped except at -4 and 2, which is what this was telling me here. So there's the domain. Every number except -4 and 2. All right, I got a few examples for division without trying to make this video an hour long. We have dividing functions and their resultant domain. We can write f of x divided by g of x, or f divided by g of x. This, again, the shorthand of that. And there's just an added piece to this domain that we've been used to. We've been talking about the overlap, f and g, the domain of f and the domain of g. We got to remember that the denominator, which is in this case g, can never be 0. So we've got to do this and make sure that this can never happen. So let's look at an example of that. We're going to do the quotient of f and g, and they're both linear. So let's write those domains. And right now we'd be thinking, well, the domain of the resultant will be all real numbers. I'm going to find out that that's not necessarily true. So let's think about writing f divided by g of x first, right, or f over g. And in this particular instance, there's really nothing else to do. I mean, we could factor something out, we could cancel something out, we could do any math here that's necessary, but there is no math that's going to be required. There's nothing that cancels. So we could circle this as the answer of f of g of x, or f divided by g of x, excuse me. But what we don't have is the domain. And the easiest way to find the domain is to just grab the denominator and say this can never, that's just not supposed to be there. So let's pretend that didn't happen. This is what I was trying to talk about. We want to grab this and bring it over here and simply say 6x minus 2 can never equal 0. We want to solve this for x. So I'd add over the 2 and then divide by 6. And we'd say, all right, x could never be 1/3. So the domain would have been the overlap of these two and with this constraint. So since the domain was all real numbers as an overlap, we've got to say, well, it's all of those except that one. And we want to write the domain right there. It's -infinity to 1/3, union 1/3 to infinity. And that is an example of a quotient and its resultant domain.